We need to talk about heterogeneous catalysts now. We've talked about homogeneous catalysts where the catalyst is in the same phase as the reactants and products. Here, they're in different phases. Usually the catalyst is a solid, and more often than not, the reactants are in the gaseous phase, and these are quite important in a lot of industrial processes. So let's look at an example here of when you get an alkene. So you've got ethene, and that will react with hydrogen. You get an addition reaction, and it will form ethane. Right, that reaction is catalyzed by nickel, the actual metal nickel. Okay, so let's see how that works. Right here, this is the surface of the nickel catalyst. And what happens in heterogeneous catalysis is you get a phenomenon called adsorption, not absorption, not absorption, adsorption. So it just it forms a loose association with the surface of the metal. So you get the ethene comes along and forms a loose association, and the hydrogen also forms a loose association. It brings them into very close physical proximity, and also by adsorbing, it weakens the bonds. And then what happens is you form ethane, and then the molecules deadsorb from the surface, and the ethane will fly off, leaving the surface of the nickel catalyst free to catalyze other more reactions. So that is how a lot of heterogeneous catalysts work. Right, now the example in the specification they say that we need to know is iron acts as a catalyst in the Haber process. So the Haber process, of course, is making ammonia. So we get N2 plus 3H2. It's an equilibrium reaction, and you get ammonia. Right, now there's a problem with heterogeneous catalysts, a phenomenon called poisoning. That's where the surface gets coated with impurities, and of course, if that happens, the surface is not available for the molecules to absorb to, the reactants to absorb to, and so the efficiency is reduced. And this is quite important in the Haber process because you use a lot of nitrogen. Yeah, the nitrogen that comes from air, and air quite often contains very, very small amounts of hydrogen sulfide. And hydrogen sulfide will react with iron to form iron sulfide. So Fe plus H2S goes to FeS, hydrogen gas, and unfortunately this will, if FeS builds upon the surface of the iron, it prevents it from it's acting as a catalyst. Another fairly good example of a heterogeneous catalyst is a catalytic converter in a car, which you did about the first organic chemistry module, the alkanes module. And so this is the reaction that it's catalytic in the catalytic converter. Right, you have so the exhaust gases, they pass over the catalyst, which is platinum, usually on a finely divided, to give it large surface area, finally divided inert support. Nitrogen oxides, such as NO2, which are made in the car engine due to nitrogen react with oxygen at the very high temperatures you get, that will react with carbon monoxide from incomplete combustion. And these are both quite nasty things that causes breathing difficulties. Carbon monoxide is poisonous, and NO2 also causes acid rain. And instead you're going to get carbon dioxide and nitrogen. So to balance that, I think I'm going to have to need 2 carbon monoxides, 2 carbon dioxides, and a half of nitrogen. And of course, these two, are not toxic. Carbon dioxide and nitrogen are not toxic. The car's catalytic converter is finely divided to give it a large surface area, and the gases pass over and react. Incidentally, catalytic converters, they can become poisoned. Up to about 20 years ago, petrol, they used to be able to get leaded petrol, which contained lead compounds. And what happened was, if you put that into a car with a catalytic converter, you'd get a very thin coating of lead on the surface of the catalyst, and that would completely ruin it. Again, it's a good example of poisoning of a catalyst. Right, finally, one heterogeneous catalyst which is mentioned in the specification, and it comes up an awful lot, and it's just a pure piece of learning really, so to talk about it. It's involved in this process called the contact process. And the contact process is you get SO2 by burning sulfur, you oxidize it to SO3, and then you react that with water to form sulfuric acid. So it's this in the manufacture of sulfuric acid. Well, this stage here, the oxidation of SO2 is catalyzed by vanadium 5 oxide, which is a solid. And of course, SO2 is a gas and SO3 is a gas. Now, the way that this catalyst works is the vanadium changes its oxidation state. So first of all, we get SO2 will react with the vanadium 5 oxide. So vanadium is in the +5 oxidation state there. And that will form SO3 and V2O4. Well, the vanadium there is in the +4 oxidation state. That's +5. Then in the next step, V2O4 reacts with oxygen to regenerate the V2O5 catalyst. So the vanadium 5 oxide doesn't change permanently in the reaction, so it's acting as a catalyst. As I say, it's a heterogeneous catalyst because vanadium 5 oxide is a solid, and SO2 and oxygen are gases.